Okay, class, today we are starting atomic structure. We're going to determine the relationship between energy, wavelength, and frequency and calculate them with 80% accuracy. We'll also calculate the change of energy using Bohr's equation for the hydrogen atom. We'll also talk about de Broglie's equation and quantization of energy. Quest Concepts 8a pairs with this quest. So first things first, we have the electromagnetic spectrum. Electromagnetic radiation has a lot of different forms. We're used to just looking at visible light. When we're looking at visible light, we all have heard of Roy G. Biv at some point or another. That is the order of the colors in the visible light spectrum. Radio waves are also included in that. In terms of wavelength, they're fairly long, which makes sense because we use the radio while we're traveling, and we often are able to listen to the same station over a pretty decent stretch of distance. We have microwaves, just like the same ones in your kitchen. Infrared. Infrared is usually valuable for identifying heat signatures. Ultraviolet, we look at ultraviolet for, you think about black lights and things like that. Ultraviolet UV radiation is also dangerous, can cause sunburn. We have X-rays. X-rays are very powerful in terms of energy. We always wear the lead vests, and then gamma rays are the most dangerous. One of the things to note is that wavelength and energy have an inverse relationship. So the longer the wavelength, the lower it is in energy. In terms of remembering the order of these, gamma rays is always the strongest. Ultraviolet is more energetic than the visible light spectrum. Remember, violet is over here, so it makes sense that ultraviolet, UV, is right after it. Same thing with infrared. We've got red at the start of the spectrum here, and so IR, infrared, is right before it and is a little bit weaker in energy. That being said, in terms of colors, colors have their own energy. Their wavelengths are still fairly small, but red is the weakest in energy, while violet is the strongest in energy. So we need to be able to look at all these things in terms of waves, because the wavelength is the shortest distance between our adjacent wave crests, or if you want to go trough to trough, this counts as a wavelength as well. You can still look at that way. Amplitude, if we're looking at amplitude, we're looking at from the axis of propagation to the top of the peak. Nodes occur when we hit 0, so these would be our nodes. All right. Now this is relevant for when we look at the structure of the atom. If you think about a Bohr model, even though the Bohr model is largely incorrect and we're not really going to focus on it too much, but for the purpose of this visualization, I'm going to show you. If we look at a Bohr model, we've got our nucleus in the center, and you've got your electrons around it. In the Bohr model, we're used to seeing these rings or these shells. In actuality, we know those rings, those shells don't exist, but they are areas of density, and we're going to look at that when we get to the atomic structure part later on in this play posit. But it's important to know that in terms of a wave, the atom functions as a wave. All of the electrons in our atom can also be treated like a wave. So the nodes, if we were to compare the wave we see here to the Bohr model, a node would occur in this open space between our rings, so to speak. Even though we know we don't have rings, we just have areas of large density. So in between the areas of high density, we would have nodes. So we would see those typically where our peaks would be. But it's still very relevant overall when we're looking at the wave. We also have the frequency. Frequency, I know it looks like a V here. It's actually represented by the Greek letter nu. So this is nu. It's kind of like a curvy V. It is the number of waves in a cycle that pass a given point per second. So they're measured in hertz or seconds to the -1. Seconds to the -1, that's the same as saying 1 over seconds, or your number of cycles over seconds. Again, wavelength and frequency are also inversely related. Frequency is directly related with energy. So if you increase your frequency, you're increasing your energy. You have more passes of the wave per second. It's going to hit you with more force because you're getting hit by more of them. You're getting bombarded with more waves in that sense. So in terms of our velocity of our wave, the speed of our wave, we can relate that to the wavelength and the frequency. So in general, velocity is equal to the wavelength lambda. Lambda is wavelength. So this is the Greek letter lambda, and it is your wavelength. So lambda, your wavelength, times your frequency, gives you your speed. Now, in terms of electromagnetic radiation, everything travels at the speed of light, which is a constant speed of 3.0 times 10 to the 8th meters per second. So we can substitute that in for our equation, and we get C is equal to lambda V. So speed of light is equal to the wavelength times the frequency. Okay. So let's do a problem with it. The brilliant red colors seen in fireworks are due to the emission of light with wavelengths around 650 nanometers when strontium salts such as strontium nitrate and strontium carbonate are heated. So they want us to find the frequency of the red light wavelength, 6.50 times 10 to the second. It's the same as 650 nanometers. One of the things with lambda always has to be in meters. So we needed an important conversion in order to do this, and you'll see that on the next page. We know that it's in nanometers. To convert to meters, there are 1 times 10 to the 9th. So I'm actually going to, I always put it 1 e to the 9th in the calculator, but I'll put it here. 1 times 10 to the 9th nanometers in 1 meter. So you can either divide by 1 times 10 to the 9th, or you could also do 650 times 10 to the negative 9th, and that would put it in meters, even though this is not true scientific notation. Either way works when you're putting your calculator. We know that C is equal to lambda nu, so we have 3.0 times 10 to the 8th meters per second, and that's equal to our wavelength, 650 times 10 to the negative 9th meters, and that's equal to our frequency nu. So we just solve for x. We end up getting that nu is equal to 3.0 times 10 to the 8th meters per second over 650 times 10 to the negative 9th meters. Meters will cancel, and we'll be left in some number per second. So seconds to the -1, or if you want to write hertz, hertz is okay. So let's do it. Let's put that in our calculator. So we've got 3.0 e to the 8th. Now, I always put these in parentheses, so that way there are no errors with your scientific notation. Divided by 650 e to the negative 9th. And we get a frequency of 4.6 times 10 to the 14th. All right, so 4.6 times 10 to the 14th. Cycles per second. It's a lot of cycles. So how does matter behave? Matter acts like a wave. When we're talking Max Planck and atomic theory, matter acts like a wave, and because of this, it has wave-like properties. He also had as his equation, the energy is equal to some integer n. In regards to the atom, we're going to relate it to the energy levels, so energy level, and then times h, which is Planck's constant. H is 6.626 times 10 to the negative 34th joules times seconds. That's Planck's constant. It's an S there, I'm sorry. And that's times the frequency. Now the energy is quantized. Quantized meaning that the energy comes in small discrete packets. So those packets are called quanta, and we're gonna treat them like packets. So packets of energy. When we're thinking about an atom, we know an atom has different energy levels. These quanta can help it move from one energy level to the next. So because of this, light can travel both as a wave and as a particle. There's this idea called the duality of light. Since light can travel as both a wave and a particle, we end up being able to calculate energy of photons. So a particle of light is a photon. Even though it is viewed as massless, it technically does have a mass. It is very, very light. But when we think about that, since light travels as a particle and it has mass, we can treat light as matter. So since it acts as a wave and a particle, we're able to do these calculations. So it's cool. You have times where light can be treated like this, or it could be a bunch of particles streaming towards you. So we can do a bunch of calculations with these. We just did one of them. First one we saw, we were using this equation here. Now you can also rearrange that equation and use it to your advantage to determine the energy of a photon. We know from Planck's equation, energy is equal to Planck's constant times nu, and we know nu is our frequency. However, we also know that the frequency is equal to the speed of light over lambda, our wavelength. So we could take this rearrangement and plug it into our equation for nu, and we get the energy of a photon is equal to hc over lambda. Some important things here, energy is in joules, specifically joules per photon, so particle. Remember, this is a particle. You'll see some applications where you'll be able to find the energy of a single particle, and then they'll ask you about moles. So you may want to remember that 6.02 times 10 to the 23rd particles, I'm just going to say particles, is equal to 1 mole. Okay. Speed of light, 3.0 times 10 to the 8th meters per second. Frequency is always in inverse seconds, or reciprocal seconds. And then Planck's constant, 6.626 times 10 to the negative 34th joules per second, or joules times second. Which makes sense. If you look at the units, you have joules times second for your h, you've got meters per second for your speed of light, and then your wavelength lambda in meters. Meters cancels, seconds, seconds, and you're left with joules. Okay. So the blue color in fireworks is often achieved by heating copper 1 chloride to about 1200 degrees. Compound emits blue light having a wavelength of 450 nanometers. They want to know the increment of energy, the quantum, that is emitted at that wavelength. Okay. Well, we know the energy of our photon is equal to h nu, right? And that's equal to hc over the wavelength. We don't need to solve our frequency in between. We can just plug it straight in. We have 6.626 times 10 to the negative 34th joules times seconds. We've got 3.0 times 10 to the 8th meters per second. And we've got our wavelength. Remember, wavelength has to be in meters, so tack on that 10 to the negative 9th there. 10 to the negative 9th meters. All right, and we'll be able to get our energy. Let's go ahead and solve this one out. So in parentheses on my top, 6.626 e to the negative 34th times 3 e to the 8th, close parentheses, divided by 450 e to the negative 9th. Boom. 4.4, I think they gave us 3 sig figs, 4.42 times 10 to the negative 19th. 4.42 times 10 to the negative 19th joules. All right. So that is how much energy is emitted per photon. So the reason this is important, the emission spectrum. Oftentimes we can apply some energy to our electrons in our atom, and when we excite them, they go up to higher energy levels, and when they fall back down, they give off energy, they emit energy. So they absorb all the energy that we put into them, and then they give off energy, they emit that energy. And when they emit that energy, it corresponds to a wavelength. And that wavelength then corresponds to a color. If you remember from Honors Chem, we had our flame test lab, where we threw a bunch of different ions in the flame, and we were able to see a nice pretty flame once we were able to excite those things. So that's the basis of an emission spectrum. So here we have the Balmer series. Hydrogen is the one that gets looked at a lot. It has several specific lines. The Lyman series is when we excite our electrons in the hydrogen, and they are excited to different levels, and they always fall back to level 1, n equals 1. That is a Lyman series. The Balmer series is when we excite those electrons and it falls back down to n equals 2. We see very specific lines for that. And then we also have different lines, a Paschen series, when we excite those same electrons and they fall back down to n equals 3. And you can see based on the picture here that those always correspond to different bands of light. So here's our Paschen series. These are the wavelengths we'll see for our Balmer series, and then we'll see some of these smaller ones down here for the Lyman series. And so we see these colors as a result when we look through a spectrometer that is able to diffract the light for us. Okay. So what's nice though is that if you look at all of those different changes in energy levels, we can calculate them specifically for hydrogen using Bohr's hydrogen atom model. He has this equation, negative 2.179 times 10 to the negative 18th joules times 1 over n squared, which is the final, so F is final, so your final resting place, minus your initial, which is your starting place. So with these types of problems, be sure to think about context. If something is being emitted, energy is being given off, so it's probably going to have a negative sign. When energy is gaining or being absorbed, if it's going up levels, absorbing energy, it's a positive sign, so just think about that. That's going to be very useful when we start to do these problems. In this example, they've got this red line going from 3 down to 2. 3 would be my initial, and 1 would be my final. So I'd have 1 over 1 squared, which is still 1, minus 1 over 3 squared, which is 9. So I'd end up getting 8/9 times that value in joules. And it would give me the discrete amount of energy needed for that particular hydrogen atom. Again, this only works for hydrogen. So let's do one. Calculate the energy required to excite the hydrogen electron from level N1 to level N2. Calculate the wavelength of light that must be absorbed by the hydrogen atom in its ground state to reach this excited state. Okay, so we know that our change in energy is going to be equal to negative 2.719 times 10 to the negative 18th joules. And we know that our final is going to be 2, so 2 squared minus 1 over 1 squared. We do the math, we're going to end up getting a positive number here. So we've got 1 squared is 4, so 1/4 minus 1 gives us a negative 0.75 times negative 2.179 times 10 to the negative 18th, so e negative 18. All right, I get 1.63 times 10 to the negative 18th. 1.63 times 10 to the negative 18th joules. So I know that's how much energy it will take me to go from n equals 1 to n equals 2. Now I also know that that energy is going to be equal to the energy that, or it'll be equal to the wavelength, not equal to the wavelength, but it'll be proportional to the wavelength that hydrogen atom must absorb. So I know I can then use this equation. 1.63 times 10 to the negative 18th joules is equal to Planck's constant, so 6.626 times 10 to the negative 34th joules times seconds times speed of light, 3.0 times 10 to the 8th. I'm going to write meters per second up here because I'm running out of space. And then over my wavelength. All right. So algebraically, I would want to swap these things. I get hc divided by my energy to give me my wavelength. So I'd end up getting 6.626 10 to the negative 34th, 3 10 to the 8th divided by 1.63 times 10 to the negative 18th. This will give me my wavelength. So let's see what we get. So I've got 6.626 e to the negative 8th, or sorry, 34th, Planck's constant, times 3 e to the 8th. And then I'm dividing it by my answer from before. And I get 1.21 times 10 to the negative 7th. If I multiply that by 1 e to the 9th, that'll give me my wavelength in nanometers. I'm looking at a wavelength of 122 nanometers. 122 nanometers. So again, what I did there, I had 1.21 times 10 to the negative 7th meters as my answer. I multiplied it by 1 times 10 to the 9th, and that put me at 122 nanometers. Okay, there we go. Go ahead and calculate this one on your own. Okay, should have gotten an energy of 4.575, or in the vicinity, times 10 to the negative 19th joules, and a wavelength of 4.34 times 10 to the negative 7th. Hey, guess what? In nanometers, that's 434 nanometers. I can tell you there is a Quest question that's very similar to this, so keep an eye out for it. Okay. Last one, we've got the de Broglie wavelength. So de Broglie came along not too long after Planck, and recently after Einstein discovered E equals mc squared, he said, hey, if E equals mc squared, then I can somehow incorporate that into this Planck's equation. And we end up getting that the wavelength is equal to Planck's constant divided by the mass times our velocity. Okay? So the key to this, though, and we have to look at units first, we got to look at the joule, because the joule is going to determine our units a bit here. We have joules per second, kilograms, and then velocity in meters per second. And that looks weird. It doesn't look like that's going to cancel out and give us meters, but it does. If I look, I know that a joule, to remind myself that a joule is equal to a kilogram times a meter squared over second squared. So I know that one of those is going to be gone from my meters per second. I know one of my seconds is going to be gone, so both seconds are gone and one of those meters is gone. And then kilograms drops out, and then I'll be left with just meters on top. So the meters do end up getting there from the units. It works, I promise. So we've got our numbers. We know that our wavelength is equal to 6.626 times 10 to the negative 34th joules times seconds. And we've got our mass of our proton, which is very, very tiny, but it's still in kilograms. They were nice to us. Kilograms times 158 meters per second. All right, we'll go ahead and calculate that. So we've got 6.626 e to the negative 34th divided by, was it 1.627? Is that what they said? 672, I'm sorry. 1.672 e to the negative 27th. Yeah. And then that is times 158. All right. And we get a wavelength of 2.50 times 10 to the negative 9th. And that is in meters. If I multiply that by 1 e to the negative 9th, or just 1 e to the 9th, 2.5 nanometers, a very small wavelength. 2.50 times 10 to the negative 9th, and I get 2.5 nanometers. Okay. And that is all for today. Well, you take a stab at one. 2.5 times 10 to the 9th nanometers. Or meters, sorry. If you want to put it in nanometers, it'd be 2.5 nanometers. All right. Go ahead and try this one on your own. Okay. Hopefully you plugged everything in and got 1.82 times 10 to the 3rd meters per second. That is all for today. Have a great day.